the top of this, you guys might recall what a chord is, because we're going to be using chords this section. So a chord is a segment with endpoints on the circle. And if a chord is not a diameter, then its endpoints are going to divide the circle into a minor and a major arc. So you may never have thought of that, but when you have a chord on a circle like this, you end up getting a minor and a major if it's not a diameter. If it's a diameter, it makes two semicircles. All right, so we're going to take this theorem and use it. And this is a really easy theorem to use. So I'm going to point out this part of the theorem. If you have two minor arcs that are the same measure, then their chords are also going to be the same measure to each other. So if the arcs are the same, then the chords will match. So if this was 50 degrees and this was 50 degrees, then the lengths of these chords would have to be the same because their arcs are the same. Okay, now this theorem works both ways. So you might remember from earlier in the year that if and only if is a biconditional. So you can use this forwards and backwards. So that would mean that I could also say if the chords match, then the arcs match. Or I could say if the arcs match, then the chords match. All right, that's a very easy theorem to use. So I've picked out a few problems that we're going to do together, and then you can go back and look at the other ones to see more examples. Okay, so let's go to number 2. So if you notice, these chords are marked the same length. That means if this measure is 1/16, then this measure is 1/16. Now, if this arc is 1/16, then we know from last section that the central angle always matches the arc. So x has to be 116 degrees because our central angle will be the same as that arc. You might read that it's called an intercepted arc. That's because it's cutting it off. So if you see intercepted, it just means the arc that's cut off from the rest of the circle. Okay, go to number 3. This one is kind of cool because we know that if these 3 chords are equal, then we know that these 3 arc measures will match. So we have to get creative here. We know the circle adds up to 360, so we're going to take 360 and minus off the 96. Okay, so when we do that, 360 minus 96, we're going to have 264 degrees left to mess around with. But we know that the 3 arcs are the same, so if we take the 264 and divide by 3, then we'll have each of those arcs that are left. So 264 divided by 3, each of them will be 88 degrees. So they asked you to find x, so x is 88 degrees. Okay, we're going to try number 4, again using the same theorem. So on number 4, you'll notice that these chords match, and if the chords match, then we know by the theorem that the arc measures have to match. So if this is x, then I can put an x there also. Okay, well you might notice that all of those together will add up to the gigantic circle. So we can take 360 minus the 90 and then divide by 2. Or some of you might want to make an equation where you add up everything to equal 360. That would also work. Totally up to you. I usually just do 360 minus 90 and then divide by 2. So that's going to give me an x of 135 degrees for those missing arcs. All right, let's skip to number 6. So in number 6, we're using the opposite part of the theorem. This shows that these arcs are the same, and if the arcs are the same, then the chords have to be the same. So if the arcs are the same measure, the chords have to match. And if the chords match, then I can make an equation. 5x minus 5 has to equal 2x plus 1 because I know they have to match in length. Okay, now I just solved that. So I'm going to get a 3x equals 6 and an x equals 2. Again, using that same theorem. All right, the last one we're going to do on this page is number 9. It's a little bit harder. It uses some other things besides just that theorem. But let's point out that these chords match. And if those chords match, then these arcs have to match. So right away, I know that W is 100 degrees. So I'm going to find that first. Then what I'm going to come over here and do is go over something we talked about in section 10.1, and I told you about this. These are both radii of a circle. They're congruent to each other. And that makes an isosceles triangle. And if I have an isosceles triangle, then my base angles have to match. So this base angle will be 35 just like that one. That makes 70, which makes this central angle 110. And if my central angle is 110, then we learned last section that the arc is also 110. So now I have y, which is 110. And then finally, I'm finding them out of order because now that I know that I have these three arcs, if I subtract from 360, then I'll have the arc that's left. So 360 minus 310 will be 50 degrees for what is left of that arc when I take away the other ones. So that's all examples of that same theorem at the top, which is pretty easy to use actually. Okay, so let's go to the next page. We're going to have another theorem and then just look at a couple of examples for this theorem. So if you have a diameter of a circle and it's perpendicular to a chord, what's going to happen is it's going to bisect the chord and it's also going to bisect the arc. So basically that diameter comes through and it cuts the chord in half and it cuts the arc in half if it's perpendicular. And then these are just opposites from each other. So this is just saying, it's kind of like the converse. It's saying the opposite from what the top one is saying. So let me show you how this will work in this picture. So it says in circle Q, the radius is 13 and RS is 24. Okay, so right away, if you look, this is part of a diameter. It's the radius. So I'm going to go ahead and just make it a whole diameter. That diameter is perpendicular to the chord. So what's going to happen is it's going to bisect the chord and it's also going to bisect the arc. All right, so it says RS is 24. That's going to make both these pieces 12 and 12 because the 24 is going to be split in half. So right away I know that RT is 12. Okay, now they would like me to find PT. Well, in order to find PT, what's going to happen is I'm going to connect, now I put the 12s in a bad spot, so I'm going to move them over here. I'm going to connect and make a right triangle. So I'm going to kind of expand this right triangle so you can see what I'm using. This is P, this is S, and then this is T. Okay, so this piece from S to T was 12. We just got that because RT and ST match. And then they told us that the radius is 13. So the piece of the triangle that I just drew in right there is the radius. That is 13. And they would like us to find this PT. So I'm going to put an X on it. So you might start seeing, oh, they're making us use triangles in this chapter. We're going to be doing Pythagorean theorem on pictures like this in order to find the missing piece right here. So I would set this up as 12 squared plus x squared equals 13 squared. And then I would solve it. So once you solve that, I'll just solve it and tell you that you get 5. That's going to make this piece 5 right here. So I'm going to put that in the picture, which is super tight in there. But this piece is 5. Now, to find TQ, what I'm going to do is notice that this is all of this is radius. So if I think about the whole radius being 13, but the piece from here to here is 5, then I can find that little piece that's left by taking the whole 13 and subtracting off the 5. So 13 minus 5 is going to be 8. So this leftover piece, TQ, ends up being 8 because I take 13 and minus the 5 off. All right, so let's kind of set up one more just to see another example of this. So this time it says the diameter is 12. It says CD is 8. Okay, well we know that the diameter comes through and it bisects the chord. So the 8 is going to be split into 4 and 4. I'll put the 4s on this side. And then it says arc CD is 84. From here to here is 84. Okay, so let's see what they want us to find. They would like us to find DE. Well, if I take the 84 and I go back up to this theorem, notice that the diameter is going to bisect the arc and the chord. So basically I'm going to take 84 and I'm just going to divide that in half. So 84 divided by 2 is 42. So this answer is 42 because you're cutting the arc in half. Now I'm going to find FD. Okay, well, FD I already found because the entire chord was 8, but it got split in half with the diameter. So 8 divided by 4 is 2. Oops, I didn't get that right. Hold on. 8 divided by 2 is 4. I said it backwards. So the whole chord was 8, and I divided it in half. Okay, and lastly, I'm going to find AF. Okay, so in order to find AF, we're going to create a right triangle. So I'm going to go ahead and draw the radius in and create a little right triangle. And I'm going to draw it out down here so you can see it. So this is AFD. Okay, so this piece, FD, was 4. And then they told us that the diameter was 12. Okay, well, if the diameter is 12, this is the radius. So that's 6. And I'm trying to find AF. So again, I'm going to be using Pythagorean theorem in my little triangle right there to find that AF. Okay, so here's how I would set it up. X squared plus 4 squared equals 6 squared. And I would simplify. Now this one is not a perfect square, so you end up getting b squared equals 20. And then you're going to square root 20, and you're going to have to simplify that into 2 square root of 5. And we'll leave it as a radical like we did last chapter. So again, Pythagorean theorem you're going to be using on these right triangles. Okay, last theorem in this section, and we'll apply it, and then we'll be finished with section 10.3. So it says, in a circle or congruent circle, 2 chords are congruent if they are equidistant from the center. So this theorem says that these chords will match if they're the same distance from the center, which makes sense because you've gone out the same distance from the center. Okay, and you can use this both ways. So notice the if and only if, that is a biconditional, so you can use it both ways. Okay, let me show you how this one would work. We're just going to do number 7. So notice that these 6's match. That means that the chords are equidistant from the center. So if TS is 21 and UV is 3X, those chords have to match because they're both 6 from the center. So I do 21 equals 3X, and X is 7. And then the last example we're going to do over that theorem is number 9, and then we'll be finished. Okay, so number 9 is harder because we have to draw our own picture. So what I want you to do is draw a big, giant circle Q. Label the center Q. And then it says chord AB and chord CD, and they tell you the 2 chords. And it also tells you that they are 6 centimeters from the center. Okay, so if they're both 6 centimeters from the center, they're going to be the same length. So when I go to draw these, I'm going to draw them roughly the same length. Okay, so I'm going to make this one AB, and I'm going to make this one CD, and then they're both 6 centimeters from the center, so I'm going to put a 6 there and a 6 there. Now, go ahead and put right angles because where the radius is going to hit them has to make a right angle if you're talking about distances. Okay, next, it says that they would like you to find AQ. All right, well, we need to put, this is Q again. We need to put our chord measures into the picture. Okay, so AB is 3x minus 2, and CD is x plus 8. So if you look at this picture, these chords are both 6 from the center. That means the chords have to match. Okay, so we're going to make an equation that gets them to match. 3x minus 2 equals x plus 8. We're going to use that to solve, and that's going to tell us how big x is. Okay, so that's going to be 2x equals 10, and x equals 5. All right, so now that we know x is 5, we're going to use that in the picture to plug back in. So I want you guys to create a right triangle. It can be anywhere you want it to be. I'm going to draw it over here, I guess, because they want AQ, but honestly it could be anywhere because all these little pieces are the same. So I'm going to connect A to Q, and I'm going to put an X on that because we're trying to find that. This piece was 6, and then I need to know how long this piece is. Okay, so I'm going to take my 5 and put it back in. 3 times 5 minus 2. 15 minus 2 is 13. So the whole chord is 13. So now you have to ask yourself, well, if this bisects the chord, then it's not going to be 13, it's going to be 6.5. Okay, so we're going to do Pythagorean theorem with this little triangle where we have a 6 and a 6.5, and we're trying to find x. Okay, so let's set up Pythagorean theorem. 6 squared plus 6.5 squared equals x. Now, since that's a decimal, then we can finish our answer with a decimal. So I'm going to do 36 plus 6.5 squared. I'm going to get 78.25 equals x squared. And then I'm going to square root 78.25. So I should get x is about 8.8 centimeters once I do that. So again, this is a little harder than you guys are going to have to do. I just am showing you how you use all the theorems together and then Pythagorean theorem at the end to solve that. You may skip these constructions. We will not be doing those this year. Okay, now I couldn't find my answer for that. Is that what you guys got for that? I couldn't find my... That was a hard question, and... Did I not stop it?